All right, so our first application then of our newfound two-dimensional vector skills is going to be with this topic called relative motion, or sometimes it's called addition of velocities. And essentially what we're trying to do with this is we are describing the motion of some object in two different reference frames. So it might sound a little bit awkward at first, but it's a relatively simple concept, and it's definitely something you've dealt with in your everyday life. So one example you can kind of think of would be just like a boat on the water, right? You can describe the motion of the boat relative to the water, but you can also describe it relative to the shoreline. And then, of course, the key thing is that the boat will be moving with respect to the water in some way, but then, of course, the water itself is also moving, right? So the water is moving relative to the ground, the boat's moving relative to the water, and so both of them you can kind of describe their velocity relative to the ground, right? Another example, we'll kind of go through, I'll show you some examples of each of these here in a second. Another common example would be a plane flying through the air, right? The plane is going to measure its own speed, its own velocity relative to what the wind is doing. But then, of course, the wind is going to be moving along relative to the ground as well with some velocity, right? And pretty much for all of these different types of problems that we're going to have, for all of these relative motion or addition of velocity problems that we're going to have, we're basically just going to use this one formula here. So there's three different parts to it. There's these three terms. We have, it is addition of velocities. So we have three different velocities that we have to keep track of. And as long as you understand conceptually which velocity is which in every problem, this is really the only formula that you need for all of these types of problems, right? So let's go ahead and look at what this means. So what I have written out is this velocity here of your object relative to the stationary frame is equal to the velocity of that same object inside the moving frame. So we have v equals v prime plus the velocity of the moving frame itself. So as some examples, right, if you're talking about boats on the water or planes in the air, this would be like your velocity of the boat or the plane relative to the ground is equal to the velocity of the boat or the plane relative to either the air or water, whatever moving reference frame it is moving through, plus the velocity of the frame, which is going to be either the water or the air, right, depending on which one you're going through. And so those aren't the only examples that we'll have. The first one I have, we'll have a person walking on train, but in general, the way you describe it is, again, the velocity of your object relative to the stationary frame is equal to the velocity of that object relative to the moving frame plus the velocity of that frame itself. So yeah, so if you have these three, and again, it is important to remember these are all two-dimensional vectors. So this is really, again, two equations baked into one another. You can do it for the x direction, you can do it for the y direction. You can see what you get. So let's go through some examples so we can kind of see what we're talking about. We'll do a very simple one first that you can probably do just intuitively on your own without me helping you, but we're going to go ahead, we're going to use our formula. I'll show you, you can obviously kind of just see what the answer is right away, but we'll go ahead and we'll still apply this situation to our formula so you can kind of get an idea for how this stuff works. So let's say that this first example that we have, we can say you are standing by some train tracks, watching a train go by. The train is traveling at 15 meters per second, and you watch someone in the train walk towards the back of the train at 1.2 meters per second, right? So the train's going along in some direction. I didn't specify which one. Doesn't really matter which. You can assume the train is moving forward in this case, right? The train's not moving backwards. You can say the train is traveling at 15 meters per second, and you watch someone in the train walk towards the back of the train at 1.2 meters per second. And you can say, okay, how fast are they walking? How fast is this person walking relative to you, right? So you have this person on the train. That's the motion you're trying to describe. So you have the moving reference frame, in this case would be the train. You have the stationary reference frame would be the ground, right? So as you can imagine, as you can guess, you probably just take, if the train's moving forward, if the train's moving to the right, and this person's walking towards the back to the left, that their overall velocity, you take 15 minus 1.2, you get 13.8. And you would be exactly right, but let's make sure we, let's stick to our formula that we have and make sure we can fill in all the details. So again, we have this. We have the velocity. In this case, we're just dealing in one dimension, right? We have the train moving in one way, and the person's walking towards the back of the train. So we're just going to do one dimension for now to keep things nice and simple. So I don't even need to put my vectors on it, my vector hats. So we have the velocity of this person relative to the ground. I'm going to call v is equal to the velocity of this person walking through the train relative to the train itself plus the velocity of the train, right? So again, you have the velocity of the object relative to the stationary frame equals the velocity of the object in the moving frame plus the frame itself. So in this case, what we would have is we don't know what this one is. This is the one that we're looking for, right? We're standing on the ground, so their speed relative to us is going to be again, it's the same as their speed relative to the ground since we are standing still. So we'll say v equals v prime, right? So v prime again must be their velocity relative to the moving frame, which is their velocity relative to the train in this case, which we're going to call negative 1.2 meters per second. You still do want to pay attention to these relative directions, right? So I've told you that the speed is 1.2 meters per second, but again, when I say it's towards the back, that means you can assume, again, it must be in a different direction than from what the train is going, plus simply 15 meters per second, right? Because the train is our moving frame, so the frame, this VF, this velocity of the moving frame, is 15 meters per second. And of course, it is exactly what you'd think. You get the final velocity of this person walking along the train as 13.8 meters per second. Again, this is just one dimension, so it's nice and simple. Let's go over a couple examples with some planes and some boats. Let's put this stuff in 2 dimensions and see how that changes the picture. So again, you are still just going to use that same formula over and over again, but it's just a matter of keeping track of all the different information you have. So now we can say, look at our next example. Make sure I don't block your view of this. We'll say that we are riding in a boat and we are moving at 6.1 meters per second relative to the water. We're going to say that the boat is pointed upstream at an angle of 25 degrees. I'll explain what I mean by upstream in this angle, just the convention that we use for that here in a second. We'll draw a nice picture for it. We're going to say that the river that this boat is on is flowing at 1.4 meters per second. What is the velocity of the boat relative to the ground, right? So what are we given here? We're given everything that we want to know about the boat and its velocity relative to the water, but we don't know anything about the boat's velocity relative to the ground, right? We're given a magnitude and a direction of the velocity for the boat relative to the water, and we are actually given everything that we would want to know about the velocity of the river itself. So let's go ahead and let's draw a picture really quick. Let's just kind of graph this out. So when I say 25 degrees upstream, the convention that I think I like to use, you can kind of draw this however you want. I'll draw my X and Y coordinates here. So the convention that I want to use is downstream is, in this case, when you have a boat on a river, downstream is just down. So I'm going to say that the river is flowing in the negative y direction, which means that our boat relative to the water is going not downstream, not upstream. It's 25 degrees pointed upstream. So in this case, it would be something like this. So we can say that this angle, we'll call it theta, and we can say that we know theta is 25 degrees. So this represents my v prime vector, right? So this one that I've just drawn here, this is my v prime. This is where drawing these pictures is going to be very helpful here in a second. Now what do I know? The river is flowing at 1.4 meters per second, so the river is flowing downward, right, in the negative y direction, which is downstream is down, upstream is up. That's kind of the convention that I like to use. So it's flowing at 1.4 meters per second, and so it is going to be going in this direction. So why am I drawing it tip to tail there again? Well, we are adding these vectors together, right? And so we need to remember conceptually what adding vectors together means. So this is going to be the velocity of my moving frame. So let's keep track of our formula here. We have the velocity of, in this case, this is our velocity of the boat relative to the ground equals the velocity of the boat relative to the water plus the velocity of the moving frame, which in this case is the velocity of the water itself. So then, of course, here's my v prime, here's my v of the frame. These two have to add together, and this will give me, as I draw it, this one down here. Still kind of moving upstream a little bit, just kind of how I have this drawn is probably what we would expect, but not quite as much, right? It's going to be, as someone on the river would see them kind of almost crossing straight across the river, whereas someone in the boat would see themselves as pointed kind of upstream in this direction, right? So we have our v, we have our v prime, and we have our v of the frame. So again, this is all in 2 dimensions. So let's go ahead, let's just write our 2 different equations, right? We have one for the x direction, and we have one for the y direction. So we're going to say velocity of the boat relative to the ground in the x direction is equal to the velocity of the boat relative to the water in the x direction plus the velocity of the water in the x direction. So that's one of my equations. My other equation will be very similar, but in the y direction. So the velocity of the boat relative to the ground in the y direction equals the velocity of the boat, relative to the water in the y direction plus the velocity of the water in the y direction. Let's go ahead. We have 6 different values here. Let's see which ones we can start to plug in. So do we know anything that there is to know about these two values? Let me move this up, make sure you can see. So do we know anything about the velocity of the boat relative to the ground? We're given this 6.1 meters per second relative to the water. This is our speed, so this is the length of our v prime. And we're also given the direction. So we don't have the x and y components, but now with all of our newfound vector skills, we know 6.1 is the length of our vector. We know 25 degrees is the angle of our vector. And so we can plug those in and figure out what our components are going to be of this v prime. Again, we don't know anything about the regular v relative to the ground. That's what we're trying to find. But we do know everything there is to know about the velocity of the water as well. So let's go ahead and start plugging these in. Vx, that's one of the things we're looking for. Vx prime is going to be equal to 6.1 meters per second times, here's my angle. So if I want the x component of this angle, of this vector here, in this case it would be cosine of 25 degrees, right? The length of my vector times cosine of 25 degrees. This will give me the x component of this v prime plus what is the velocity of the water in the x direction? Well, again, as I have it defined, the water is going in the negative y direction. That's the direction of the river. And so this is simply 0. So right away, we can do this, and we already know what the Vx component is. Let's go ahead, let's write this out for Vy as well. We have Vy is going to be equal to 6.1 meters per second times the sine 25 degrees, right? So this will give me the opposite. This will give me the vertical component of v prime plus vfy, but we know the water is moving down, right, as we have it defined. So it's minus 1.4 meters per second. So now with this, we just have to plug some stuff into our calculator. We can do our trig, we can figure this out, we can figure out what our different components are for this boat. The velocity of the boat relative to the ground. So the Vx is going to be 6.1 times the cosine of 25 plus 0. And so this is just simply about 5.5 meters per second. Vy, you do something similar. We have 6.1 times the sine of 25 minus 1.4. You end up getting about 2.6 meters per second minus 1.4 meters per second. And so this Vy ends up being about 1.2 meters per second, right? And so at this point, if this, if I were to ask you on this homework, and you just gave me the x and the y components, that'd be fine. You would be done. Just to show you though, I did ask for the velocity, so this is all the information about the velocity. But if it makes you feel better, you can also write it in terms of, so this is the x component, this is the y component. We can also write it in terms of the magnitude and direction, just for some practice. We can say the overall velocity, the overall speed of our boat is going to be 5.5 squared plus 0.2 squared. And make sure it's still in meters per second. Take the square root of that, about 5.6. The angle that we have, right? This is just from our Pythagorean theorem. The angle that we have, the inverse tangent of 1.2 meters per second over 5.5 meters per second, and this gives us an angle of about 12.3 degrees, right? So if we go back up to our picture here, again, as I have it drawn, it's roughly about halfway in between. It was a 25-degree angle as our direction relative to the water, but again, someone watching on the shore would say that we were only moving at a 12.3 degree angle upstream, right? All right, let's do one more example. This time we'll have an airplane flying through the air, right? Okay, so for this problem, we're going to say we have an airplane pilot wants to fly due north. Oops, make sure you can see it. There is a 65 kilometer per hour wind to the east. And so we're going to ask, what direction should the pilot point the plane if the plane's airspeed is 340 kilometers per hour? So now again, we're given some different pieces of information here. Let's go ahead, let's write our equation, let's draw our picture. So again, of course, as always, we're going to start with this. Velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of our moving frame, which in this case is the velocity of the air itself. Let's go ahead and let's draw our picture again. In this case, the convention, you would say north is positive y and east is positive x. So you just do your north, south, east, and west, and use those for your x and y directions when we're specifying this. Again, you don't have to do that. That's just the convention, so that's how I'll usually solve these problems. So let's go ahead and let's draw this. Let's make sure we understand what exactly we're solving for. So overall, our question is, what direction should the pilot point the plane? So I'm going to be solving for some sort of angle, right? So let's go ahead. What do we know about these vectors? So the first thing we're told, an airplane pilot wants to fly due north, right? So we can assume that they mean, they're flying due north relative to the ground, right? If you're going to navigate from one airport to the next, you want to know, those are points on the ground, so you need to be able to know what your velocity is relative to the ground. So I don't know exactly how fast this pilot is going to end up going relative to the ground. I don't know what that speed is going to be, but I do know that their overall velocity relative to the ground, the direction of it, had better be north, right? We're trying to get it north. That's the whole goal of this. So we better set this direction north. I don't know what the length of this vector is, but I do know the direction of this. So we're going to say this, our velocity of our plane relative to the ground, had better be pointed straight north. What else do I know? There is also going to be a 65 kilometer per hour wind to the east. So I'm going to draw it like this. I kind of already know ahead of time how I want to draw this. You might have to think about it for a second when you're doing a new problem. But this is going to be, so the east again, what we're going to say is to the right. This is going to be the velocity of my frame. And so, of course, then as you expect, if there's a crosswind pushing us to the east, we do in fact have to point our plane slightly west, right? So so the pilot is going to point the plane relative to the air, both north and west. And then with this eastward wind, the overall velocity relative to the ground will end up being straight north. So this would be my v prime, right? And so of course, as we said before, we have this equation here. We can check it with just our definition of adding vectors, just from a graphical standpoint, from a drawing standpoint, right? We have v prime plus vf, add them tip to tail, does give us our overall velocity relative to the ground. Okay, so now again, we do definitely have two dimensions here that are going to be relevant, as we had before. So let's go ahead, let's break this up into our two different equations that we have. We can say what we have: Vx equals v prime x plus Vfx. And then we can also, of course, say Vy equals Vy prime plus V frame y, right? So of course, again, our object is the plane. It has a speed relative to the ground, it has a speed relative to the air, and we also have the speed of the wind itself, the speed of the air, right? So let's go ahead and let's start filling in what we know. So Vx, right? Again, we have 6 of these, so we've got to be able to figure out 4 of them, right? We have 6 variables, we have 2 equations. When you have 2 equations, you can solve for 2 different unknowns, right? If I have 2 equations and 3 unknowns, I need something else. I need some other piece of information. But in this case, we have 2 equations, 6 unknowns, so we've got to be able to pick out 4 of these different things from here, assuming we want to solve for everything there is to solve for. So let's go ahead, let's start filling this in. The velocity of the plane relative to the ground in the x direction has to be what? Well, we've got to be going north. North is our positive y-axis, so this had better be 0, right? So that is one thing I know right away. This is basically saying, right, the speed of the plane in the x direction, right? The speed of the plane eastward and westward relative to the ground had better be 0, right? Because we need to have our plane. The whole point of this problem, the whole thing that we're trying to solve for, is we want our plane to be pointing straight north. So you have 0 equals, what is this one? We have v prime x plus v frame in the x direction. So v prime x is going to correspond to what? This is again, the speed of the plane relative to the air. So what do we know? Well, we're told the plane's airspeed, so that's a good start. But this is just the x component of that, right? So let's go ahead. We're going to write something like this. We need to start defining these angles. So here, I'm going to call this angle theta, and this is ultimately going to be the angle that we are looking for, right? So I'm going to define this angle from the y-axis. This is going to kind of change how I do some things. I'll explain exactly what's going on. So I can write it like this. I can write my Vx prime as 340 kilometers per hour times, I want the x component of this V prime here. The x component is going to correspond to, in this case, because I've defined my angle from the y-axis, this is a case where the x component actually corresponds to sine of this angle, right? So when I define it from the x-axis, x is cosine and y is sine. When I define it from the y-axis, you gotta do your SOHCAHTOA, right? As we've all gone over in high school. So the opposite side of this angle is, in fact, when I look at just this v prime vector here, the opposite side of this is, in fact, my x direction. Right? My adjacent side is now going to give me my y component. Okay, so we have this. We have 340 kilometers per hour times sine of theta, and then we have plus what? We have plus the speed of the wind in the x direction, which is going to be 65 kilometers per hour. So actually, at this point, I'm going to keep going. I'm going to solve for the overall velocity of this plane. But at this point, again, if this was a homework problem and all I wanted was the direction, this formula here is all you'd have to do. You could actually just leave this this formula for the y direction alone, right? Because look, we know this is 0. We know this is 340 times sine of theta, right? This is our length of our vector. In this case, this is our airspeed. Speed is the length of our velocity. We have times sine of theta plus 65, so this is actually solved, right? We just have to do our algebra and solve for this theta. So we can go ahead and do that, but let's just solve for everything just for this example so we can make sure we understand how to do all these different pieces, get some more practice in. Let's go ahead and let's write out our y equation as well. So I'm going to have to kind of separate these here for a little bit. So we have in our y equation our v in the y direction. Do we know anything about that? We don't know what our speed in this direction is going to be. We know that we're going to have, it's all going to be in this, right? This one's going to be 0. This one's going to be something in the north, but we don't know what that one is going to be. This one, our prime speed in the y direction is going to have to be what? 340 kilometers per hour times, in this case, the cosine of theta, right? So I'm looking at my v prime y. Take the cosine, the adjacent side of this vector adjacent to the angle is going to be this. And then what is my wind speed in the y direction? It's 0, right? This wind is just blowing straight eastward. It's not blowing north or south whatsoever. So with this, we can then pretty simply, with these two equations, we can pretty simply solve for both. We already know what the Vx is. We can solve for the angle, and we can solve for the Vy as well. Let's go ahead and solve for this angle first. Uh-oh, whoops. Something's going wrong here. There's one correction that I need to make to this. What would that be? So let's look at this equation here. Based on how I have this angle defined, there is one extra thing that I need to add in. So this plane, relative to the wind, is flying both north and west. But how I have west defined, west should be negative in the x direction. So this is positive in the x direction, right? This is east. This one should be negative in the x direction, right? So we do have to add in, I did not write it down when I first wrote this equation, but you do need to add in this minus sign, right? To denote that this is in the negative x direction, right? As long as these are different directions, you'll get the same answer, right? You just have to pick one positive, one negative. The convention is put east as positive. You don't have to do that. But the main thing is that these are in opposite directions, right? The wind is blowing to the east, so the plane has to be angling itself to the west slightly, right, in order to end up flying straight north. So we have it this way, right? The good news for us is this will still cancel out. So when we add this over, then it becomes a positive again, and now everything will be okay. So we have sine of theta is going to be equal to 65 kilometers per hour divided by 340 kilometers per hour. You can do inverse tangent, just like with the others. You can do inverse sine, you can do inverse cosine. So we have our theta will be inverse sine of 65 divided by 340 40. In this case, I can just go ahead and cancel out these units, right? Sine is a ratio. The angle should be unitless, so you better get a ratio here where the units are the same if you're going to do that. Make sure those cancel out. So you have 65 over 340. This gives you an angle of about 11 degrees, right? So there's 11 degrees. Sorry, I'm writing off the screen here. So we have this angle here. This theta is 11 degrees. So I'll write that here. And we do need to specify this is 11 degrees west of north is how you would denote it, right? So again, it's 11 degrees to the west of the north direction based on how I have this written. You could also say, this would be an awkward way to do it, but it would still be correct. You could also say it's, what would that be, 101 degrees north of east, right? If you wanted to define this angle from the x-axis, that would also kind of flip around how you're going to do your sines and cosines. But if you wanted to define this whole angle, you'd say it's 101 degrees north of east, right? Is another way that you could write that. This makes more sense to me. This is my preferred way of doing it. But if it makes more sense to you to always define your angle from the x-axis, that's okay too. Just make sure you understand how it changes when you use sine and when you use cosine. So we'll have our angle 11 degrees west of north. We can go ahead, we can solve for Vy as well. Vy is going to end up being 340 times the cosine of 11. And so what we end up with is about 334 kilometers per hour, right? So this will give us our overall speed. This will give us our overall direction. The problem originally did not ask us for the entire velocity. It just wanted to know what direction should the pilot point the plane. Now you know the plane is going to have to angle itself about 11 degrees north of west, and then that will kind of have it flying along at this angle, right? It's pointing itself to the west. The wind will blow it east. So overall, this plane will end up going north 11 at 334 kilometers per hour. So these will be very similar to the homework problems that you have. So again, it really is just this overall review for these addition of velocities. It is this formula here over and over and over again, right? There's a lot of different things you can do with it. Again, there's 6 different variables in here if you're doing this in 2 dimensions. And so you can be given any 4, right? You have to just understand and kind of match up the physical situation to the math of what variables correspond to what. You have your velocity of your object relative to the stationary frame equals the velocity of the object relative to the moving frame plus the velocity of the frame itself.